Hello and welcome to my CCNP version 8 Enterprise Core Networking lecture review. My name is Arthur Solomon and I'm going to be providing you lecture material for the ENCOR 350-401 exam. So this is going to be several video lectures covering the individual modules or lessons for the CCNP material. So let's jump in and let's see what we can do. Chapter 6 is all about IP routing, so we're going to be covering the essentials of what is entailed in that route table. Looking at routing protocols, path selection, static routing, and any type of virtual routing and forwarding that might also be present. So again, routing protocols, looking at the major routing protocols, both interior and exterior. So a routing protocol is what allows the routers to share route information. The router, specifically a layer 3 device, performs routing, meaning path selection, or figuring out how to transmit data packets from one network to another using information. That information is that route table. Routing, it's all about being able to identify the path and the path selection. So in the routing protocol overview, we're going to be talking about distance vector, the algorithms, the enhanced distance vector, link state, path vector algorithms, and which algorithms are in each category. It always is interesting because when we get into the nitty-gritty of a router and the router's function, it's essentially to move data packets from one network to another to determine the best path and how to go from source to destination. The router will use its information that it's obtained either directly connected or statically assigned or dynamically assigned to appropriately identify the paths. So the router will learn about the non-attached networks through, again, static manual configuration or through dynamic routing protocols, i.e. learned from a neighbor. Dynamic routing protocols will distribute items such as network distribution, network configuration, network information between any of the routers that's attached to it. Now, how the dynamic router protocols function are going to be dependent on the individual routing protocol. For example, OSPF, which is one of the main open standard routing protocols, it shares different information than, let's say, Cisco proprietary EIGRP routing protocol. So that's why we have to understand the different types of routing protocols, because they all kind of share information and work slightly different. Networks that are interconnected routers and are related to system managed under a common administration is typically known as an autonomous system, or an AS number, sometimes referred to as a routing domain. Basically, I look at these as spheres of domain or spheres of management. And that'll make more sense on the next slide. So we may have, let me grab my pen, one company with one AS number, and that is going to be different than another company's, but they still have to be able to share information. So there is a way to identify the different spheres of who manages them. And these are all going to be typically interior. And then between each AS number, we're going to have an exterior. We're going to get into these types of terms in a few slides, but the big thing there is understand that we have interior and exterior protocols, and we have a number of different protocols as well. Common routing protocols are things like Routing Information Protocol, RIP version 2. There's also RIP NG. Oh, misspelled RIP. That will be for IPv6 NG. We also have our EIGRP, which is also a traditional IPv4. There is a newer version for IPv6. Same thing for OSPF. Then we have ISIS and BGP. In our level of understanding of what we need to know, in reality, we're looking at, let me go ahead and erase everything off the screen. EIGRP, OSPF, BGP. These are the three main routing protocols. EIGRP and OSPF are the common interior. BGP is the most common exterior, but can also be an interior gateway as well. With the exception of BGP, everything listed here is known as an interior gateway protocol, IGP, and they're optimized for routing within the same AS number. That's what allows you to identify if it's an interior or exterior. All right, after we get past that, we have the different forms of routing protocols. Basically, what sets them apart? Distance vector routing protocols, such as RIP, will use and advertise their routes as vectors, where the distance is a metric or a cost. With RIP, they use hop count. So if we're trying to figure out the best path, when we're looking at RIP, they're using the metric hop count. And the path will be the next hop router in the destination. So we need to understand these two terms. Distance. The distance is the route metric to reach the network. Vector is the interface or direction of each network. So I'm going to draw out a new network so we can really understand this. All right. Not the best drawing. So let's assume we have 10 gig all the way through the bottom. Source, destination, A, B, C. How do I get from source to destination? Well, if RIP is being used and RIP's metric is hop count, the shortest hop count is going to win. So going from source to A to destination, that's only a hop count of 2. While below, we have 3 hop counts, or 3 hops. What's the best path? Well, we are using hops to identify bests, so source to A to destination. They may be a slower link speed, but when the metric is hop, that's what we do. So that's why it's important to understand the metrics. How are we identifying what's good and what's not? All right, lastly for this slide, when a router receives router information from its neighbor, it will store it in a local routing database, and the distance vector algorithm will also be used to determine the appropriate path to ensure the best loop-free path to its reachable destination. The route table, I'm going to keep saying this, the route table will only identify the best path. There might be multiple paths, but the route table will only identify the best path. And if, for whatever reason, that best path no longer is available, the route table can update itself to the second best path, and it will only display the best path. So if the primary best path goes down and the backup becomes the now new primary, the route table will only display the up-to-date version best path. All right, so let's go ahead and move on. Now, it's also important to point out that distance vector does not just have RIP. There are other protocols in there. For example, EIGRP is also a distance vector. And it will actually use the diffusion update algorithm, or DUAL, and that's part of the enhanced distance vector algorithm for EIGRP, and it will use that to calculate the shortest path to a destination for a given network. EIGRP will advertise the network information to its direct neighbor, as other distance vector protocols will also, but there are some modifications. First of all, it offers rapid convergence time to change the network topology. So if a modification is there, EIGRP actually can do this a little quicker. It sends updates only when there is a change in the network, and it doesn't need to send the full routing table. It only does periodic updates, as other distance vector protocols do. That's important. Let's go through that again. It sends updates only when there is a change in the network. It does not need to send a full routing table update in a periodic fashion. It only does that when there is a modification or a change. That means it could be a little bit more efficient on bandwidth usage, not having to send updates when there is no relevant update. EIGRP will also use hello and hello timers to form neighbor relationships, just as a link state protocol would. So basically, it will verify its neighbor with hello timers. Basically, send a hello message. After X amount of hello messages are not received, then we can assume the neighbor is down and go for that. EIGRP will use bandwidth, delay, reliability, load, and the maximum transmission unit size instead of hop count for calculation. It has the option to use load balancing traffic equally or unequally against paths. So what does that mean? Basically here, we are acting to a calculation to determine the appropriate path source to destination, including bandwidth, delay, reliability, load on the link, and the MTU size. These calculations will be used instead of hop count, and there's actually a calculation that normally is presented, but we will get to the calculation when we talk about EIGRP as a dedicated module, instead of just an overview of this routing protocol. Alright, since we talked about our enhanced distance vector, now let's go ahead and move on to our link state algorithms. So a link state dynamic IP routing protocol advertises the link state and the link metric. Let me grab my pen. Link state and link metric for each of the connected links and directly connected routes. So all links and direct connected routes for every router in the network. That's a big thing. Each router is going to have a complete map of what's going on. That's part of how link state functions. The two main link state algorithms are OSPF and ISIS. These are the two main protocols used in enterprise. In reality, OSPF is the big one that I keep seeing. They send advertisements called LSAs, link state advertisements, while ISIS will use the link state packet LSPs for its advertisements. In reality, for the CCNP level exam, you are learning LSAs. The router will receive advertisements from the neighbors and store it in what's known as the link state database, or LSDB. From here, the state information will be advertised to each of the neighbors, all of the existing routers that it knows about, and it will be exactly as it was received. This enables all routers of the network to have an identical map of the network. Again, this map will be on each router. Any update, the map will get updated and then redistributed to all the other routers. All of the routers in a link state algorithm protocol will have a complete map. There is the SPF, the shortest path first algorithm, that is being ran on every router in the network in order to calculate the best paths to keep everything loop free. There is also an algorithm to identify who's going to be a designated router or main router or master router, which we'll get into those types of concepts in the dedicated chapter on OSPF. If you're going through this material, you should know that OSPF does have a designated router and a backup designated router, because that was all entry-level route protocols, so you should have already have known that. So now we have our distance vector, our link state. Now we also have our path vector. Path vector, which is what BGP is, it's similar to distance vector, but the difference is that instead of looking at the distance to determine the best path, it will look at various paths attributes. BGP path attributes include AS path, multi-exit discriminators, MEDs, the origin, next hop, preferences, atomic aggregates, and aggregators. So basically, when we're doing this, it actually will build out a table to figure out where it needs to go, and it has a number of attributes it needs to review. In this figure, we are looking at a loop prevention method to figure out how to get from A to B. Well, in this regard, how to go between all of the different routes. So this is one of the algorithms that will then be used to figure out the appropriate path. And you'll start noticing it will start building paths that will show, router 3, router 2, using all of the attributes. And again, we have a dedicated module just on BGP. All right, so moving on, we have our path selection. Routers will identify the path, and they will evaluate the prefix length, and it will be saved in the forwarding information base, the FIB. The FIB is programmed through the route table, which is also known as a RIB, the routing information base. This section will cover the prefix length, AD, metrics, costs, multipathing, and load balancing for both equal and unequal costs. So first one would be path selection in terms of the main components. Prefix length, AD, metrics. So the prefix length will be the prefix length represents the number of leading binary bits in the subnet mask in the on position, basically identifying the ones that are on in the subnets. Next would be administrative distance, AD, and this is a rating of the trustworthiness of the routing information source. Not all routing protocols are trusted. Not all routing protocols are trusted over all networks. So having a lower AD does mean that you're a little bit more trusted. So if a router learns about a route to a destination from more than one routing protocol, all the routes will have the same prefix length. Then we can look at the administrative distance or the trustworthiness to figure out which path to take. Third is the metric, and this is a unit of measurement used for a routing protocol to determine best path calculation. Metrics will vary from one routing protocol to another to aid in whatever is the appropriate best path. All right, so let's get into our prefixes. So again, the prefix is looking at the number of bits that are turned on. So normally we call those the ones on our subnet. So assuming that the router has the following information: 10.03 with a /28, 10.03 with a /26, 10.03 with a /24. So I'm going to go ahead and break down these three addresses. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So for the /24, 5, 6, 7, 8. 1, 2. All right, that's the slash 26. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4. So they have the first 3 octets, all ones, in common. 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. Looking at the 4th octet with that slash 24, we have things that slightly aren't. So we can look at this to figure out the summarization. Summarization would just be a slash 24. But we're not looking at the summarization. We're looking at the individual links. So that is what allows us to figure out the next hop, is looking at where the last one is. So each of these routes have a prefix route or simplify prefix that has a different prefix length subnet mask. 255, 255, 255.0, 255, so that would be the 255, 255, 255.0, 255, 255.255.192. And I don't want to do math for the slash 28, but again, you can see that there's clearly a different subnet for each one of these. That allows us to figure out the appropriate rib for it to go through. The routes are considered to be different destinations and will be installed into the rib, also known as the routing table. The route table will also include the exit interface or egress interface, and the next hop, and outbound interface, unless the prefix is connected to a network, such as in the table. Here we can see the prefix, the range, next hop, exit interface. If a packet needs to be forwarded, the route will choose the appropriate path based off of the prefix length, where the longest prefix length is always preferred. Meaning, we're looking at the most amount of ones in the prefix to identify which is the preferred path. The rib will then calculate through the combination of the routing protocol, metric, and AD the appropriate path. So we keep saying things like AD, but what exactly is that? We said it was trustworthiness. But there are actual values associated with this. If it is a static route, it's assumed to be highly trusted. If it's a summary route, it's given a trust value of 5. If it's EGP, external, trust value of 20. If it is an internal EIGRP, 90. OSPF's 110. If it's an external EIGRP, is 170. If it's an internal BGP, it's 200. In reality, static EIGRP and OSPF are the big ones for you to know and memorize. Those are the ones that are most commonly associated with an internal or IGP. Internal to an organization. If, for whatever reason, you may need to do an external gateway protocol, you're looking at BGP, and that's slightly different. The rib accepts and rejects routes based off of the following actions or logic. If the route doesn't exist in the rib, the route is accepted. If the route exists in the rib, the AD must be compared. Routes with the lowest AD value are installed because they're considered to be more trusted. Routes with a higher AD value are rejected, and the submitting routing process will be notified. You could also do a installed backup route by giving it a higher value so that when the routing table is displayed, it will display the current up-to-date route table. If a path goes down, then the backup path with the extra weight can come into play. That's one way to do weighted distributed routes that will have backups. Past that, we have our ADs. So in this example, we have our AD routing protocols, EIGRP, OSPF, ISIS, AD is 90, AD value of 90, AD value 110, AD value of 115. So what that means is it's going to look at all three of these to determine the best value, which will be the lowest. That's the one that will be sent to the route table, rib or route table. It will be based off of the lowest value. The routing protocol or protocols that fail to install the route will hang on to the route and tell the routing table process to report them if this path fails. So these become alternates or backups routes. So if this path ever fails, we have alternates. We have backup options. So a good question is, what happens when there are equal cost multipathing? What happens when the paths are the same and the routes are the same? So we do need to be mindful of this. The logic for selecting the best path for a routing protocol, again, varies depending on the routing protocol. Each routing protocol, or IG, will prefer an internally learned route over an externally learned route, and further prioritizes the path within the lowest metric. We already established that. If a routing protocol identifies multiple paths as the best path and supports multiple path entries, well, which route does the router install? It will install the maximum number of paths allowed per destination. This is known as an equal cost multipathing, ECMP, and provides load sharing across all links. All of the major current routing protocols support this load balancing for multipathing. Meaning if there's two paths that both have the same metric and the same costs, then ECMP can be implemented. The ECMP will provide the mechanism to increase the bandwidth across the multiple paths by splitting traffic equally between the two links. So in the diagram below, you can see that between R1 and R3, they're load balancing between R2 and R4. That's because the metrics are the same and the link costs are the same. So this will allow us to double the bandwidth by putting data through both. But what happens if there are unequal costs? What happens if one is greater or less than the other? By default, the routing protocol installs only a single route with the lowest path. However, there are routing protocols like EIGRP that can be configured to allow for multiple routes within the different path metrics, meaning you can have two paths, different metrics with EIGRP if you configure it. This allows us to install unequal cost load balancing across multiple paths. The traffic will be transmitted out the router's interface based off of the path metrics in the ratio to the other interfaces. Meaning if one is significantly greater than the other, it will determine an appropriate ratio and then send X amount out that interface and X amount the other interface. This allows us to load balance. So in the figure below, R1 and R3 are the source and destination, and we are splitting between R4 and R2. Most amount of data will be sent through R4. It's going to have the lower metric, so it will have probably the better ratio of sending data. So not all routing protocols can use the unequal cost load balancing. EIGRP is currently the main one that allows for this if you configure it correctly. Alright, so that is for our dynamic routing. Now let's move on to our static routing. Static routing requires zero network bandwidth because implementation is manual. The administrator or the engineer or the architect will have to implement the routes directly on the devices themselves. That also means that the directly connected routes aren't going to be propagated to the other routers unless you do something about it. Because routers are not communicating, there is no network intelligence. If a link goes down, SOL. The other routers are not going to know if a directly connected or statically configured route on router A, for example, is up or down unless it's shared with other routers. So this section we're covering directly attached static routes, recursive static routes, and fully specified static routes. Static routes are useful when dynamic routing protocols can't be used, a small network. Routes learned from dynamic routing protocols need to be superseded. Oftentimes I use a default static route to propagate a dedicated pathway that I want out of my network. That's a good use that I have found. They can also be classified as one of the main three: directly attached, recursive, fully specified. So we're going to cover these kind of all in depth. So directly attached static route. That's where a static route that uses the outbound next hop interface, known as a directly attached static route. The outbound interface will be specified and must be in an up-to-date, and it also must be up-to-date and have an up status for the route to be installed in the RIB. Normally, you're going to see this. Let me grab my pin. Next hop. The router is going to be able to determine if the next hop is up and available. If this link goes down, then that means the next hop isn't available. So configuring a directly attached static route to the interface will use ARP. Ethernet networks are huge with this. This might cause problems and it's not recommended. The router must repeat the ARP process for every destination that matches the static route, and this will consume a lot of compute resources, both processor and memory. In a large network, instability. Router is not going to be able to handle it. So if we're dealing with a point-to-point serial interface, they don't use ARP. So static routes can be directly referenced to the outbound interface of the router. Up here with ARP, that was because it's an Ethernet-based network. Down here, P2P using serial interfaces. So there are slightly different options here. Directly attached static routes are configured with the command IP route. IP route. The network, the subnets, the one that you want to match, and next hop details. Again, this should be a fairly simple review from your CCNA because CCNA in 2 modules, they went over static routing, configuring static routes using the IP route command. Here's an example. We are configuring a static route to that destination, and that's the exit interface. You can use an exit interface or next hop IP address. It really just depends. And here is 2 routers, one route going that way, one route going that way. R1, R2. Here is the destination for R2. Here's the destination for R1. That way, data can flow back and forth. If you only happen to do one, for example, let's say you only configured R1 to send to R2, well, it doesn't know how to return. So that's why you have to do both sides. It has to know how to get back. There has to be a path back. Recursive static routes, this is where the forwarding engine on a Cisco device needs to know the interface an outbound packet should use. Egress. What interface should egress occur? A recursive static route will specify the IP addresses of the next hop. IP of the next hop, not specifically the interface, but the IP address. The recursive lookup will occur when the router queries the RIB to locate the route towards the next hop IP address, whether that's learned via directly connected, manually entered via static routes, or even dynamically learned. It will then cross-reference the adjacency table to determine which IP address, which interface. The recursive static routes are configured with the command iproute network subnet next hop IP. So when you do iproute destination IP, destination subnets, next hop IP, we can call that a recursive. Recursive static routes require the router's next hop address to exist in the route table to forward the addressing using the default quad zeros. Exist in the route table to install the static route into the RIB. A recursive static route may not resolve the next hop forwarding using our quad zeros. The static route will fail next hop reachability if we're using the quad zeros, so it won't actually implement it into the route table. Recursive static routes don't use quad zeros. All right, let's look at this. Here we have the same type of setup. We have our IP route, source and destination, except we're using IP addresses instead of the egress interface. When we do our static routes, again, there are names for each type of static route based off of how it egresses. A fully specified static route will be very similar to our last two types of static routes, except IP route, destination subnet, and it will do both the egress interface and the IP address. That way it's 100% making sure it leaves out the correct interface and going to the correct IP address. Specifying the next hop address along with the physical address removes the recursive lookup and doesn't involve ARP. So there are reasons to use fully specified static routes, even though that they are very specific and very unique. So we talked about the three main types, but I said something earlier about adding a wait to a routed protocol. That way we have a backup. Well, you can do the exact same thing with our static routes. So let me grab my pen. Here we have our traditional IP route, destination, subnets, our egress point, whether IP address or interface, and then we have a number at the end. Those are our floating static routes. Remember that a static is a default value of 1. That will be the most trusted. If we add in a backup route of a value 10, well, this would not be displayed in the route table until there's the primary static route that was put there happened to fail or is no longer showing up status. It would be removed from the route table, and then it would look to see if there's a backup route. And in this example, we could have a backup route. Static null routes. Configuring a static null route on a specific interface provides a method for dropping network traffic without requiring the configuration of an ACL. Basically, creating a static route to null 0 is a common technique to prevent routing loops. So, how does this look like? Well, you could do a trace route, and you could see the path. You can configure our traditional quad 0. You can configure multiple static routes. And here we have it sent to the null 0 interface. basically that's a non-interface. It won't process that traffic. It will just discard it. So to prevent the routing loop, a static route is added to point to the generic null interface. It's just a way to not have to do an ACL, not have to worry about the processing of data traffic to that interface. Then we have other addresses like our IPv6 static routes, similar to our IPv4 static routes, except here we're doing our IPv6, turning on IPv6 routing, and then we're using the same general structure. IPv6 route, destination subnets, and our egress point. That's how we set up those static routes. Alright, lastly was our virtual routing and forwarding, also known as VRF. This is a technology that creates separate virtual routers on a same physical router. The router interface, route table, and forwarding table are completely isolated between the individual VRFs, preventing traffic from one VRF to forwarding to another VRF. All router interfaces belong to the global or parent VRF until they're specifically assigned to a user-defined VRF. So let's jump into this. So let's explore that global VRF again. So every router will have a VRF that will maintain a separate routing table. It's possible to allow overlapping IP address ranges for these VRFs. The VRF is identical to regular routing tables that are non-virtual routing forwarders. So that's something that's really important to understand, that these are virtual components that still are underneath a global or parent routing forwarder. VRF creates a segmentation between the network interfaces, subinterfaces, addresses, and routing tables. So each VRF is going to maintain their own separate tables. Configuring a VRF on a router will ensure that the paths are isolated, security is then increased, and encrypting specific traffic or all traffic on the network isn't necessarily needed to maintain privacy between the VRF instances. You can, but you don't have to, because for each VRF instance, they are essentially separated. Here we have our traditional global routing table on one interface. We can do the creation of multiple VRF instances that will require the global configuration command VRF definition, VRF name. Sadly, I do not have a hardware device that would actually allow me to show you or demo this yet. But you can also then set up underneath each VRF name, you can define submodes, and those commands would be address family, IPv4, IPv6, based off of your requirements, and is required to specify the appropriate address family. The VRF instances in the associated interface with the common VRF forwarder underneath the interface configuration submode. So in the diagram, we can see that we have a VRF management that's attached to a separate interface. Here we have the global router interface. Let me grab my pen. On gig 01 and leaving out gig 02. Well, we have on gig 03 our interface, our VRF interface management. So setting up the VRFs, we have to follow a general rule. The steps are: create a multi-protocol VRF routing table using the VRF definition and give it a name. Initialize the appropriate address family with the address family, either IPv4 or IPv6, or both if that's determined to be the most appropriate option. Step 3, enter the interface configuration submode and specify the interfaces to be associated with the VRF instance by using the command interface ID. Again, all of this will be underneath our VRF submode. Associate the appropriate VRF instance to the interface or subinterface by entering the VRF forwarding, give it a name, and underneath that mode will be done through that submode. Next would be the configuration of an IP address, either IPv4 or IPv6, on the interface or subinterfaces by entering either IPv4 subnet or the IPv6 addressing along with the secondary base command. So, what does this look like? We have not really been able to configure it, so what does this look like? Here we have our global interfaces, and here we have our management interfaces. So let's look at how that looks on a router. Here we've set up 3.1 on our gig01 interface. Here we've set gig02 to be the 10.0.4.1. So these are going to be our global interfaces. Then we need to go ahead and set up our VRF definitions. Here we have definition MGT. Notice the sub interface or sub mode. That allows us to set up the IPv4 addressing. And then we rinse and repeat for we rinse and repeat for the next interface. Again, making sure that we list the appropriate IP addresses. So I'm going to erase some of this. So these three right here set up the definition. Oh, sorry. This sets up the definition. This sets up the interface. Then we are forwarding that to our management. And then we set the appropriate IP address. Then we do the next interface, the next forwarder, and the next interface. We are working on getting some labs that actually coincide with this, but again, we will have a much deeper conversation about virtual routing and forwarding in a subsequential video. So when we're looking at our routing essentials, that's kind of the bare bone. We've covered all of the major areas: routing protocols, distance vector, link state, the algorithms, looking at basic terms for routing protocol, our fib, our rib, our ADs, looking at our static routes and dynamic routes, which protocols are in each one. We also looked at how to configure directly attached static routes, recursive static routes, and fully specified static routes. And that's it for this module. Questions, issues, thoughts, concerns, definitely feel free to reach out. Thank you. Alright, so that wraps up this module. If you have any questions or concerns, definitely feel free to reach out. Post a comment, ask a question. Remember, as we're going through this material, it's common to be able to take some time, gather your thoughts, ask some questions so that we can really work on retention and getting you more familiar with the material. Thank you.